Hello everyone, welcome to Dakshana e-classroom program. So in last lecture we started about the fluid when it is flowing, understanding its behavior, or that is hydrodynamics. So we saw like some basic definition related to hydrodynamics or ideal fluid, incompressible fluid, and non-viscous fluid, is it, and laminar flow and all that. Then we saw some like, because we need, when some, let's say, fluid is flowing through a pipe, then we need some relation between different parameters, different quantities. For that we discussed about equation of continuity. So equation of continuity is based on conservation of mass, and the equation that we discussed was like rho 1 a1 v1 equal to rho 2 a2 v2. This is mass flow rate. If you're dividing it by rho, then we get a into v, or a1 into v1. That is also called volume flow rate. So volume flow rate is constant or mass flow rate is constant if we are taking density to be constant. And then we saw more relations about energy, and that like kinetic energy, potential energy, and work done by pressure force. And then conservation of energy principle, we got Bernoulli's theorem, that is pressure plus half rho v square plus rho g h is equal to constant. This is called pressure energy plus kinetic energy plus potential energy per unit volume per unit mass remains constant. Let's continue here onward with the application of Bernoulli's principle. Regarding this, I just solved one small problem that if we are having one pipe placed in horizontal plane and with varying cross section, so let's say at one point cross section area is high, other point cross sectional area is low, then we understood that by continuity equation, when cross sectional area will be small, velocity of fluid flow will be higher, and vice versa. At a point where the cross sectional area will be higher, velocity of fluid flow will be lower. Next things comes about the pressure relation between 2 points. One is having high velocity, another is having low velocity. This too we derived with the help of Bernoulli's principle. We saw that at one point when the pressure is low, the velocity is low, pressure will be higher, and if pressure is velocity is high, pressure will be lower. That is what we discussed up to last class. Let's continue. So here some application like attraction between two closely parallel moving buses or boats. So what happened here, let's consider this is a river, and boats are moving parallelly in river. So let's say this is one boat moving with some velocity, let's say v1, and another boat here moving with some velocity v2. Then what do you think, like, just forget about this boat. The fluid layer which is in contact, which is in close contact with the boat, will have high velocity compared to the fluid layer which is like far away or comparatively away from the boat. So here velocity will be higher, here velocity will be higher, and similarly in this region. But when two boats are coming closer, is it, then you can see the velocity at this point will be higher compared to here, and let's say this is I would say v1 prime, or let me write it's v0, and here some v0 prime, is it? So v0 prime. So the velocity at this point and velocity at these 2 points, so compared to like this point means some point in between the boats and buses, compared to this point, we can say here v0 will be higher than v0 prime, because it will have cumulative effect, velocity of both the boats. So that's why like we can expect here velocity is higher. What will happen in that case? Velocity is higher, and then pressure will be, we know, actually we saw at one point when velocity is high, pressure will be low, and velocity is low, pressure will be high. So at this point, is it, at midpoint, is it, or at in between the boat or buses, the velocity of water or air is higher than on one side of boat or buses. That will result in, if I say this is P naught pressure and this is P naught prime. So this implies P naught will be less than P naught prime because here velocity is low, here velocity is high. So that because of that they will net experience pressure force, attraction force between two boats and buses. This is what exactly, this is the same condition. That's why like when train comes at some platform, is it, and high speed, the air, let's say this is a train coming on this, so the air which is in contact with the train will have high velocity. So that's why one person standing here in the nearby region sometimes feel, is it, attraction towards the lane, railway line. So that's it's advised to stay away from the train when it is coming at higher speed, because even when you are holding tight there is possibility that the pressure beside the train will be low because of high velocity of the air coming in contact with the train, and then you may feel some attraction and you may fall on the track. So that's why stay away. So these are all things we can understand with the help of Bernoulli's principle. Another way is working of aeroplane. So how exactly, like I was telling you that how exactly aeroplane, that too it's like too heavy and still it is able to fly, and like how it is balancing the weight. So some wings are there actually in the aeroplane, and normally the shape of wings is like this, and depending on like how it is exactly holding, like so plane is flying actually in the air, you can see with respect to plane the air is blowing, is it? So air, it's like it will be flowing like this way and here, is it? Now depending on if the aeroplane foil is in this orientation, is it, then what will happen actually, if this is the, like we with the help like that pilot, it control it actually the angle of this aeroplane foil and aeroplane wing. So it can sometimes make its orientation like this, it can make its orientation like this, is it? So in this situation what will happen, if the orientation of the aeroplane wing is like this, you can expect most of the air is passing on top of it, and very small air will be passing from this bottom surface. So in this situation what will happen, velocity here will be higher, right, then pressure here will be low, okay? And similarly here velocity is so let me mark this point, this is point 1 and this is point 2, and similarly point 1 3, let's say point 4. So in this diagram if I look at it, is it, or in this diagram, so let me tell you first here. So in this case we can expect mostly high speed air will be passing through the top of the aeroplane wing, is it? So in this case V3 will be higher than V4, and we can expect here V4 velocities, because very less, like almost all the air is, it will be directing it to go on the top of the aeroplane wing, is it? Very less air, and we can expect the velocity, because high speed air will be passing from the top, so velocity at lower point will be low. So because V3 is higher than V3, this implies we can expect P3 will be less than P4, is it? So here pressure P4 and here pressure P3, and so this result in net upward force on the aeroplane wing, right? And because of that it ultimately this provide lift to aeroplane. Clear? So here velocity low, here velocity high, pressure low, pressure high, net upward force, and that is how plane balance itself. So let's say in the next orientation, or you can say initially it will be net upward force acting, like if it's like more oriented, it may accelerate upward, it may go down up. In another orientation, if we are like maintaining it like just normal, in that case there may be possibility like the pressure here is little bit higher than this. In that situation it will be just staying there in the air, is it? Next condition, if like we want to land the plane, then we can increase it, we can increase this angle more, this theta can be increased. In that situation mostly air will be passing through the bottom. In that case velocity at this point will be higher than velocity at this point, so it will experience what? More like less pressure here, high pressure, and it will feel net downward force. So that way actually aeroplane wings, the angle of aeroplane, with the help of changing the angle of aeroplane wing, we can provide a lift, upward force, downward force to the aeroplane, and it can fly up and down actually. So this is the working principle of aeroplane, that too we can understand with the help of Bernoulli's principle. Similarly, you might have seen sometime the rooftop of some building, some homes get like, is it fly off when high wind blow over it. Let me tell you what exactly and how that happen also. Okay, next application is blowing off rooftops by windstorm. Sometime like what happened, let's consider here, this is one home, and so this is the rooftop. What will happen when some wind is blowing at very high speed? So we can say, let's say v is the velocity of the wind, and here velocity you can take almost, it will be equal to 0, because no wind will be like blowing from inside. So here the pressure is p and here pressure is p naught. Then what we can see, at this point pressure is like velocity is very high, so pressure will be very low. So you can expect p is less than p naught. So because of that, because if the room like it's a rooftop of some home, inside velocity of the air will be very low, is it? So when windstorm is there, velocity of air on top is very high than low. And that result in very high pressure, low pressure here and high pressure inside. That implies P less than P naught. This result in net upward force on rooftop, and because of that simply rooftop like sometime blow off, it simply move out of this home. So this is how we can understand with the help of Bernoulli's principle also. Next is action of atomizer. It is used in basically carburetor and you scent spray, paint gun. So all these like this atomizer is used, and what is that exactly and how it work out. So here we have one like cylinder. This is a cylinder, one piston is there and one tube, and there is the tank, liquid tank, in which some liquid is filled. So when we are pressing this piston, basically this piston is pressed, air inside here will be blowing, it will be moving with very high velocity. So air through this tube will be moving with high velocity, so pressure inside the tube will be like becoming very less, and that push this liquid, or you can say the lift the liquid, because here pressure will be low, pressure will be high, so the liquid comes out and it move out, and it come with the high velocity air, and that become like spreaded in the form of drops and atoms, small like drops, and that is the working principle of atomizer. So that is how your spray or scent spray, paint gun and carburetor, all these things work based on this principle, and we can understand that with the help of Bernoulli's principle. So here you can say, understand, when piston is pressed, the air flow with high velocity, high speed through tube, that result in low pressure and lift the liquid from tank, and it also mix with high speed air. So that is how actually the action of atomizer also works. These are some of the applications. There are more applications. Let's continue, and that is like quite important point about this chapter, fluid mechanics. So I hope you are understanding these things to here. Okay, next application is Magnus Effect. What is that and how does it happen? Let me tell you. So first thing is, when a spinning ball is thrown, it deviates from its usual path in flight. This is called Magnus Effect. Now you should understand how and why it deviates actually. So let's look at it. Now see, so here we have a ball which is spinning like this about its axis. This is the axis, and simultaneously it's moving in this like direction forward. So what do you expect? You will expect it to be moving in this straight horizontal line. But what will happen actually, just see, because here this ball is spinning, so because of that, if we look at the net velocity of this point, it will be like v plus r omega, and here net velocity will be v minus r omega. So the air which comes in contact with this ball, it will be like moving with, try to move with this much velocity. So you can expect the velocity of air moving here will be like proportional to this, and velocity of air moving here will be, let's say, v1, and here v2. So v1 will be proportional to this and v2 will be proportional to this. So what will happen actually? This implies you can expect v1 is greater than v2. So at this point, speed or velocity of air, is it, in close contact with this spinning ball will be higher compared to this point, is it? So velocity at this side will be higher because, and this implies p1 will be less than p2. So p1 is less than, so what will happen? Now this ball will experience, now you can see this is p2 and this is p1. p1 is less than p2, so net force on this ball will be like in upward direction, or if it is like horizontal direction, you can see like from here I can say it will be towards up actually. Then what will happen, instead of going from like in this straight line, it deviates from its path, something like that, and it will be going in this direction. This effect is termed as Magnus Effect. Why this turn out, I think you should be clear even with this also now. So as because of spinning, the velocity of these 2 points is different, so that result in the air which is in contact with this ball will have different velocities on both the side, and that ultimately from Bernoulli's principle I can say velocities are different, pressure will be different, and this difference in pressure will apply some force on this ball. If this is higher pressure, lower pressure, so net ball will experience upward force, and because of that it turns. This actually play an important role. It plays an important role in tennis, soccer, etc., these games, and cricket. Because by providing proper spin, we can change the direction of the ball in proper or desired direction, and that way like it will be moving in that particular direction. So this effect is called Magnus Effect. And why this happened, why the ball turn in one direction, how does it turn, that is the important thing you should be understanding. We can understand that with the help of Bernoulli's principle. Okay, next of its application is Ventimeter. Ventimeter actually, okay, up to now we have seen that through a pipe fluid is flowing, and we told the velocity of the fluid is v1, v2, v3. If it comes to you like, okay, let me say in a pipe fluid is flowing, and I want like you tell me that what is the speed, what is the velocity of fluid flow at any point, how can you tell me that, how can you measure that, is it? So for measuring that we have one device that is called Ventimeter. With the help of that we can measure the volume flow rate, and we can also measure the velocity of fluid flow, and that also work based on Bernoulli's principle. Let me tell you what is exactly Ventimeter and how it work, and how with the help of Ventimeter we can calculate the volume flow rate and velocity of fluid flow. Okay, next application is Ventimeter. So it is an apparatus basically, or you can say it is a device based on Bernoulli's principle, and the volume flow rate or velocity of fluid flow. So what is that exactly? It consisting of two pipe of cross-sectional area. Let's say these are two pipe of almost same cross-sectional area, area A, and these two pipe connected by a narrow tube of cross-sectional area here A. Let's say A1 and this is A2. To measure the pressure difference between these two points, a manometer tube is connected. This tube is to measure the pressure difference. So definitely we know actually here velocity is, let's say fluid flow is V1, here velocity is V2, then pressure at this point will be higher, pressure at this point will be lower. So the liquid level in these tube will have different heights. Pressure is here low, so it will be like high, pressure high, it will be like low. So this difference in height we can directly measure from this manometer tube, and let's say pressure at this point is P1 and pressure at this point is P2. So the difference in pressure can be easily measured by this manometer tube. Manometer tube, one setup is this, another setup is also there. I will tell you how exactly. That is also like simple, where like one tube is connected in here and another tube is connected here. So the same liquid basically rises. Here pressure is high, so the liquid will rise up to more height compared to the here pressure is low, liquid will rise up to less height. So again the difference in height is measured by basically, and that gave you the difference in pressure. So here instead of that I am using a manometer tube, and here mercury is filled, so rho m is the density of mercury. With this setup, so we understood this like, and pressure difference we can easily measure from here. Area of cross section we can directly like measure by our screw gauge and vernier caliper, like in inter diameter and all that. So we have all these things, and then we need actually volume flow rates. So how we can, so data here, it's area of cross section A1, area of cross section A2, velocity V1, velocity V2, and pressure P1 and P2. Let's apply now Bernoulli's principle between point 1 and 2, this narrow tube and wide tube, is it? So let's apply Bernoulli's principle or Bernoulli's theorem between point 1 and 2. Now at 1 I can write it's P1 plus half rho V1 square plus rho GH. So this is at same horizontal level, so this rho GH term will simply cancel out. P2 plus half rho V2 square plus rho GH. This term simply cancelled out, we are left with this, and now P1 plus half rho V1 square equal to P2 plus half rho V2 square. Bringing it this side, P1 minus P2, this is equal to 1 by half rho. This is V2 square minus V1 square. Okay, we got it up to here. Then P1 in minus P2, pressure difference will be equal to what? So difference in pressure we can measure. So here definitely pressure P1 will be higher compared to P2, and we can directly by manometer tube we can measure rho mercury into G into this difference in height of this mercury level in two tubes, that is rho mgh. And by continuity equation continuity equation, I can write A1 V1 is equal to A2 V2. This implies V1 can be substituted as, or I can calculate either one, V1 or V2, that doesn't matter. So we can substitute here V2 also, A1 by A2 multiplied by V1. Let me substitute it here. P1 minus P2 half rho. This V1 is V1 square minus V2 is this A1 by A2 whole square into V1 square. V1 can be taken out from here and this will be 1 by 2 rho. This is A2 square minus A1 square divided by A2 square multiplied by V1 square. Pressure P1 minus P2 I am substituting from here, and this implies rho mgh equal to half rho V1 square A2 square minus A1 square divided by A2 square, and sending all these terms down and just rearranging for V1, we get it. This is rho m gh divided by rho multiplied by, this is A2 square minus A1 square divided by A2 square and whole under root this. So we got here the velocity V1. By this, if I am substituting here, then I will also get the velocity V2. Next, volume flow rate, that will be equal to A1 into V1. So this multiplied by A1, we will be getting this is then I can get basically volume flow rate. So this is equal to simply under root, I can write it 2 rho mgh multiplied by A1 square divided by rho A2 square minus A1 square divided by A2 square. Let me just check the calculation. This is up to here, and then A1 V1 equal to A2 V2, substituting V2. So this is A1 V1 divided by A1 by A2 into V1, and this is difference in pressure. V1, I did mistake. It will be actually here V2, so it will be, I need to substitute here. This will be minus, this will be plus, because I am substituting here V2. So this, and then here some difference will be there. It will be K, A1 will be plus, A2 will be minus this, and here minus plus, and here minus plus, and denominator it will be A2, that's correct, this, and here also it will be minus plus. So let me rearrange it. It will be A1 and it will be A2. So this is the final expression. So you can see with the help of this setup, we can actually get the velocity of fluid flow at this point also, and we can get velocity at this point, and volume flow rate can be also calculated with this. You need to remember this formula, and that you can derive also easily. This is also important formula, and this is all about the Ventimeter application of Bernoulli's principle. Let's see more application about it. Okay, so see one application of the concept we just learned. Here one problem is given: water flow through a horizontal tube of variable cross section. This, the area of cross section at A, this is A and B, it's given as 4 mm square, and here it's 2 mm square. And if 1 cc of water enter per second through A, find speed of water at A and B. So means volume flow rate is given as 1 cc water is entering 1 cc per second, I can write, and volume flow rate is equal to area into V1, or it can be A2 into V2. So by using that, we can get directly answer for A and B. And area, because the volume flow rate is given centimeter cubic per second, so we need to convert that into centimeter. So it will be like area is, I will write AA, this is equal to 4 into 10 raised to power minus 2 centimeters square, and similarly AB will be 2 into 10 raised to power minus 2 centimeter square. By using this relation, 1 cc per second is equal to, this is 4 into 10 to the power minus 2 into VA. This implies VA is coming out to be 1 by 4 means 100, that is 25 centimeter per second. Similarly, solving for VB, we get it's 1 by 2 into 10 to the power minus 2, that would be 50 centimeter per second. So we are getting the speed of water at A 25 centimeter per second, B 50 centimeter per second. Next, it's saying the pressure difference PA minus PB. So pressure difference, we can calculate that with the help of Bernoulli's principle. C part, pressure difference. So we can have PA plus half rho VA square equal to PB plus half rho VB square, because height h both will be same, so we'll cancel out simply, and this implies we are PA minus PB is equal to 1 by 2 rho into VB square minus VA square. And if I convert that into meter, then it will be like VA is equal to 1 by 4 meter per second, VB is equal to 1 by 2 meter per second, and density of water we know 1000. So PA minus PB is coming out to be 1 by 2 into 1000, it's 1 by 4, 1 by 2 whole square VB minus 1 by 16. Simplifying it, it will be 1000. So 1000 divided by 2, simplifying it will be like 3 divided by 16, and it's like 3000 divided by 32, this is Pascal. So that is the delta P pressure difference. We can even simplify it further also. So delta P solving, we are getting it this, and this is all simple application of the concept. Let's see more. Okay, let's see one more problem. So a horizontal pipeline carries water in streamlined flow at a point along the pipe where the cross-sectional area is 10 centimeters square. So here the cross-sectional area is 10 centimeters square. The velocity of water is given as 1 meter per second, and pressure at this point, so I will write P1 is given as 2000 Pascal. And the pressure of water at another point where cross-sectional area is, this will be, so at this point we need to find pressure. This is the problem. So that also seems straightforward, easy problem. First, we were given, let's say V1 is given 1 meter per second and A1 is given as 10 centimeter square. A2 is given as 5 centimeter square, but V2 is not given. By simple equation of continuity, I can write A1 V1 equal to A2 V2. This implies V2 is equal to A1 by A2 multiplied by V1, that is 10 divided by 5 multiplied by 1, comes out to be 2 meter per second. So we got the speed of water flow at this point. Next we need pressure at point 2, so that we can like straightforward now. It should come in your mind that we will be getting the pressure at point 2 by using Bernoulli's principle, right? So next, by Bernoulli's principle, between point 1 and 2, if we apply, then solving it, we are getting, this is P1 plus half rho V1 square, this is P2 plus half rho V2 square. P1 2000, half rho 1000 multiplied by 1 square, this is equal to P2 that we need plus half rho 1000 into 2 square, right? Simple substituting. So this we got 2000 plus 500, P2 plus it will be 2000, cancelled out, P2 is coming out to be 500 Pascal. So this is the simple problem, simple application of Bernoulli's principle. So like, I don't think you should have any confusion anywhere. We just need to understand the problem exactly in just get the relation between what exactly it is asking and what is given to you in the problem. Try to correlate them, use corresponding relation and substitute the values. Solving, you will be getting straightforward answers. So these are simple some application of Bernoulli's principle. Let me talk about more. Okay, so next application of Bernoulli's theorem is the speed of efflux. This is also termed as Torricelli's theorem. And what exactly it is, let me tell you. So let's consider this is a tank which is filled with some water or maybe some other liquid, and one hole is made here. So let's say it's filled up to here with some liquid, and small hole is made here. Let's say this distance, this is small h, and I'm taking this complete level as capital H. Okay, what is efflux? Efflux means flowing out of some substance or liquid, is it? You can say or water. So that is termed as efflux. Speed of efflux means at what speed it will be flowing out. So here we are considering one container which is filled up to some capital H height from the bottom, but a hole is made at some height and the level of the liquid in the tank above the hole is small h. I can write this is capital H minus small h. Then we will see that exactly on what factors the liquid it will be coming out from here. So the speed of this liquid coming out will depends on what factor. We will see, we are going to derive. This is the V is called speed of efflux, is it? So speed of efflux means the speed with which liquid will come out from the opening. The speed with which liquid will come out from opening. Right? So how we can calculate here? We will use some assumption here. First, let me write the area of cross section for this is A, or let me write it A naught. So A naught, area of cross section of small opening in the tank. And I'm taking this total area as capital A simply. So A is area of tank. Which area? I mean this area. Just take care of that. So A is this open area of the tank or circular open area. That is taken as stem. This area is taken as, and one more assumption here that we take is capital A is very greater than A naught. So A naught is very small. With this assumption, if I apply Bernoulli's principle continuity equation, so speed is, let's say, V, and here if I take some U, then I can write A naught into V is equal to A into U, and because A is very large, so A naught by A will be very small, so we take, this implies U almost taken as 0. Right? Now one more thing, again this is also we are going to derive this relation by using Bernoulli's principle, but how we use, where exactly we use reference, something like that, that is important things. You need to focus on that exactly. So because we define some height, is it? So height, you can take actually the reference this line also, or you can take reference this line. From both the line you will get exactly same expression. It will not differ. If you want, I can do the calculation, otherwise it will be simply cancelling out, it will not. Okay, let me do the calculation by taking this as my reference line for potential height. Okay, another point, and pressure just outside this opening will be like pressure here, you will be taking here, so pressure here will be equal to what? P naught, and at this point also it will be equal to P naught, atmospheric pressure. Is it pressure just outside the opening will be taken as P naught atmospheric pressure. Now we can apply, so let me take, this is point 1, this is point 2. Point 2 means this opening. Okay, point 1, at open surface of tank, and point 2, open side of small orifice. Is it, or a small opening on side? So now apply Bernoulli's theorem between point 1 and 2. Okay, so now I can write P1 plus half rho V1 square plus rho GH. I'm like H1 equal to P2 plus, or let me substitute directly the values. So P1 here, it's equal to how much? P naught rho V1 square, because I am taking this velocity almost equal to 0, so it will be 0. If I am writing it from this reference, then it will be rho G into capital H. Clear? And at point 2, again pressure comes out to be P2 is P naught plus half rho velocity V square plus height of this is rho G capital H minus small h. I hope there should not be any confusion. I am writing it from this reference. If I would have taken the reference here, then this will be rho G small h and this will be 0. So the expression will still come exactly same as we will be getting from here. So no difference will come. P naught gets cancelled out, and remaining we are left with rho. Let me cancel rho also. So this is simply 0. Then I am left with G capital H. This is equal to V square by 2 plus G capital H minus G into small h. This is also cancelled. This implies V square is equal to 2GH. That implies V is equal to under root 2GH. You see something here, interesting thing. If some body fall from h height, then also it will attain same velocity, is it? So this V is equal to free fall equal to velocity of a body attaining on free fall for h displacement. And like if a body is allowed to fall freely from h height, then whatever the speed it will be gaining, that is the exactly speed we are getting here, where h is the height of this liquid level above the opening, right? This relation was first time derived by Torricelli, one scientist. So this is also called as Torricelli's theorem. This relation is also termed as Torricelli's theorem, and that is like simple thing. With the help of application, how we get exactly that should be even clear. Some assumption I am taking here, you should keep those things also in your mind. I am taking in this situation, this area is very large compared to this area, so that's why I'm able to take the velocity of this open, like is it liquid level is very 0. I'm like very small or almost taken as 0. So with the help of that we are getting this expression. It's still not over. Let me erase and let me tell you few more things about this concept. Okay, so finally we got the velocity of efflux or speed of efflux. It comes out to be V is equal to under root 2GH. where h is what? Height of liquid level from the opening. So this is opening, that this is h, is it? H is height of liquid level in tank from the opening, and we can see V is directly proportional to H. Means if you make a hole even lower, at lower level from like top or at side like near to the bottom, the H will increase. So that's why we can expect the speed of efflux. So in this case, if it is like falling here, if I'm making that speed will be even larger. This doesn't guarantee the range will be actually higher. That will depend on some other factor, I will tell you. But we can expect here, let's say if we have different holes, let's say here V1, and from this it's V2, and from this it's V3. So we can expect here, this implies V3 will be greater than V2 greater than V1, as H for V3 will be higher, right? Okay, so this is about one thing here, because V is directly proportional to under root H. Next, so if I am considering, let's say this is a height small h, and it's falling finally on the base level, then this height will be equal to what? This is capital H minus small h. So time taken for the liquid to fall on the ground, time taken by liquid to fall on the ground, that can be calculated, because here we are getting this velocity V equal to under root 2gh. This will be only horizontal. So in vertical direction you can just stick to one small particle of fluid. So this small particle of fluid will have only horizontal velocity. In vertical direction, displacement it need to cover is capital H minus small h. Acceleration is g, and uy is equal to 0. So for a fluid particle is it coming out from opening, I can take uy equal to 0, ay equal to g, and sy is equal to capital H minus small h. This implies I can write sy equal to capital H minus small h is equal to uy plus half into t plus half ay into t square, that is equal to 0 plus half gt square, and this implies t we are getting under root 2 times capital H minus small h by g. So this is the time taken by the fluid element to fall on the base level, or on the like time to fall up to base level. That is better description, because ground sometime the tank may be capped at some height. In that situation it will not be the time to fall up to the ground level, so it is up to base. So like by the time liquid is coming out and falling on the base, it is also traveling some horizontal distance. We call it range actually, or displacement in x direction, displacement along horizontal direction. So displacement of liquid along horizontal, this can be written as displacement. So here we got how much time it is taking, what is the velocity, that is this vx. So this range equal to x equal to, you can write vx into time to fall, and vx we know actually it's under root 2g small h, time is under root 2 times capital H by small h into g. Just multiplying it, we are getting it 2 under root small h into capital H minus small h. This is the expression. So if a small hole is made at a height h below the top level, At that point of time, the liquid will be falling, striking the base level at a distance of 2 under root small h into capital H minus small h. So R, we are getting under root, this is 2, R is equal to 2 small h capital H minus small h. Next come is, can we comment when like it will be maximum, because sometimes that is also asked, so we can differentiate that and we can get answer for that too. So R square is equal to 4h into capital H minus small h dr, so 2r dr by dh, 4 this is capital H minus small h, and differentiating this by product rule, and plus small h, differentiation of this will be minus 1, this is equal to 0, and this implies h minus small h minus small h, that implies h equal to capital H by 2. So for this value you will get the maximum displacement of the tank, like water level or liquid. It will strike the base level at maximum distance, so R will be maximum if hole is made at small h equal to capital H by 2, and we can get R max, that is equal to 2 small h capital H minus small h, substituting the value 2 h by 2, h minus h by 2, and h by 2, this comes out to be basically capital H, so R max is equal to capital H. So this is a little bit more about, first thing is speed of efflux, the speed with which the liquid will be coming out. We understood that is equal to simply under root 2gh, where h is the height of like opening from the top liquid level in the tank, and this is your h. It depends, like the speed v is directly proportional to under root 2gh. It does not depends on the liquid, in what liquid it is filled in this tank, is it? It's a viscosity, and like on all these things, like it doesn't depend. Viscosity you cannot say, because here we are applying all these relations only for ideal fluid. That's, you should keep those things also in your mind, because for real fluid things changes actually. So this is all for ideal fluid, but yeah, we can say that the speed or velocity of efflux does not depends on fluid. Velocity of efflux does not depends on the liquid, that which liquid is filled in the tank, and this, and the time to finally strike the stream to the base level is this, and how much distance it will travel along the x direction horizontal, we are defining that R, that comes out to be this. For R to be maximum, we should keep this made this small opening at it higher, like from the base also you can take h by 2, or either from the top also it's capital H by 2. So this is all about speed of efflux. There comes sometime like here, how much time it will take to empty the tank. So if hole is made up to here, then it will be like only able to empty it up to this level. So we can, if made this hole here, then it will be like can empty the complete tank. So wherever like we are making the hole, how much time it can take to empty the tank up to that much level. Let's check the calculation. Let's get the result for that. Okay, so let's calculate time taken to empty the tank, and here I'm assuming initially the tank is filled up to full level, and this is capital H. So let's say at time t, at time t, the level of liquid is up to height y. So at time t, this is the level of liquid in the tank. I can write this is, let's say, y, and I have made the hole here exactly at the bottom. So at this moment of time, it will be coming out with the speed of 2 gy, right? Simple concept to calculate this result is that the volume flow rate, the rate at which volume is coming out, flowing out, liquid is coming out, that can be written as A naught into V. This is equal to the level at which it is falling down in this. Is it a volume of the rate at which the liquid level is decreasing in the tank? Is it? So the volume flow rate from opening can be written as dV by dt is equal to A naught into V, that is A naught under root 2GY, right? And let in time dt from t to t plus dt, liquid level in tank fall by dy. Then the level is it the rate of decrease of liquid in tank, that I can write what A into dy by dt. This is the velocity multiplied by area, and because it will be negative, dy by dt will be decreasing, that's why it will be negative, so I may multiply it with one more negative. Now this is positive. Now because why this level is going down? Because it's coming out in this, so these two quantities must be equal. Simple thing, is it? So the rate of decrease of liquid in tank must be equal to rate of flowing out of liquid from opening. Simple, and that means A into dy by dt minus should be equal to A naught into under root 2GY. Now we need to ultimately simplify this relation. So this is, we need dt, so dt I can write equal to A by A naught dy by under root 2GY. This is A by A naught under root 2g into dy by root y. Integration minus sign will be there, 0 to t, and this let me write it h to h prime. If I make h prime equal to 0, then it will be the time taken to completely empty the tank. So this side we are getting t minus A by A naught under root 2g, and integration of this, I can write it y power half, that is equal to y power like minus half, so it will be y power half divided by 1 by 2, minus half plus 1. So this implies limit 0 and like capital H to H prime, substituting it, so it's coming out to first 2 A by, this is A naught under root 2g, and substituting the limit here, it will be under root h prime minus under root h, absorbing minus inside, t is coming out to be A by A naught, taking the root under root 2 by g, this is under root capital H minus capital H prime. So this is the time taken to empty the tank from H level to H prime level. Time to completely empty the tank, then H prime will be simply 0, that is coming out to be T naught A by A naught under root 2H by G. This is the answer. So this is about you must be clear that how we are calculating, what is the approach we are following, but you are not supposed to remember that. You are not supposed to learn the derivation completely. You are supposed to remember these results finally. A by A naught, what is A here, what is A naught here, you must be clear even with that. Under root 2 by G and bracket under root capital H minus under root capital H prime. This is the time to empty the tank from this level, from here to, let's say here, H prime is up to here, and if you want complete, then it will be this one. So theoretically this is all about this chapter, actually fluid mechanics. I hope you understood things. We need to solve some problem based on it. You try more problems, and I think like you should not have much doubts and problems, and like things are, because this is easy chapter. I don't think like there is any confusion, but still we will see with your doubts, and that's all. Thank you.